Okay, hello. This is a continuation of probability rules, probability laws. We had some microphone issues in the last video, and I think we were at this part right here. What does A complement intersect B complement represent? Okay, so in the picture here, I've drawn out the intersection of the complement of A and B. And it's everything that's outside of A or B is what it turns out to be. So it's everything outside of the union of A and B. Okay, so what does A complement intersect B complement? That represents here the members who are neither lawyers nor liars. Okay, that's what that set represents, or that's what that event represents. And the probability of A complement intersect B complement is the number of outcomes in that event divided by 100, because there was 100 in our sample space. Okay, so looking at the picture here, if you recall, we found that there was 70. I think that was a 20 there. There was 70 in the union of A and B, and so that means there's 30 outside of A and B. Okay, so there's 30 that are neither lawyers nor liars, so that probability is 0.30. Okay. Last question with this example here is, are events A and B mutually exclusive? Remember, mutually exclusive says something about, is there any two events are mutually exclusive if they have no outcomes in common? And well, because we have 10 members that are lying lawyers also represented that way, there's 10 elements in that event, that that set is not empty, so there are outcomes in common. So the answer to this is no, they are not mutually exclusive. No, there is overlap between the two. Okay. All right, so that wraps up that example. Moving along, a new idea to think about probability. We want to look at probabilities in the case that a special restriction or condition is in place. Okay. So here, let's think about this idea of a conditional statement versus an unconditional statement. Two examples here. What is the chance that Alex Rodriguez gets a hit? Well, that's an unconditional statement. All right, and in fact, that chance can be thought of as his batting average. A conditional statement says, well, what is the chance of Alex Rodriguez getting a hit given that there are men on base? And so this extra condition or restriction to the problem can affect that chance or that probability. So we think of that as a conditional probability or conditional chance in this case. And ESPN is, well, Alex Rodriguez is retired now, but for all baseball players, or for most baseball players, they have this sort of information. They have their batting average, and then they have their batting average when men are on base. Okay, and those are potentially different. Another example here is, what is the chance of developing skin cancer? So every person has a certain chance, but suppose now you know a little extra information, that a person has had a dozen or more sunburns in their lifetime. What does that chance do? Well, that chance goes up. That's what the physicians tell us. And so with this conditional information, that changes this probability. And so we want a way to handle that. And this notion, this definition here of conditional probability allows us to think of these sorts of probabilities that have extra information in them. The conditional probability that event A occurs, given that B occurs, is given by this expression here, P of A with a vertical bar B, and we usually think of that as given, P of A given B, and it's defined as the intersection probability, that is the probability of A intersect B, divided by the probability of B. And we are going to, let me move this out of the way here, we're going to force P of B to be non-zero because we can't have 0 in that denominator. And so the Venn diagram here that represents now the new sample space and an event of interest looks like this. So before it was a square that represented S, and A and B were in it, but now what I've done is I've said given B has occurred, I'm interested in the chance of A. Okay, so B is this circle here. That has necessarily occurred. What is the chance that I see A? Okay, so that's shaded area there within B is what I'm after here. So what we're doing is when we condition on B, our new sample space becomes B. Okay? Because we're assuming that B has occurred. And a way to think about that is if you were to compute the chance of Alex Rodriguez getting a hit given there are men on base, you would only look at situations where there are men on base to get that particular batting average. So given that scenario, you're restricting yourself just to that. The multiplicative rule, next, another definition here, and this is just an algebraic consequence of the conditional probability rule. If you were to take the conditional probability rule and algebraically solve for this numerator here, the intersection probability, you would get P of A intersect B times P of B, which is what this expression is here. Now this other representation you could get by, if we applied the conditional probability rule on the probability of B given A, we're switching the conditions, that would be again the probability of A intersect B, but now we would divide by the probability of A. Okay, so the event that you condition on is the one that you divide by. So I've conditioned on A, so I'm dividing by the probability of A. Okay, so if I took this and algebraically isolated the numerator there, the P of A would come over here. I would have P of A times P of B given A, and that's what that representation is there. So both the conditional probability P of A given B and P of B given A yield this multiplicative rule here. Alright, so let's apply some of this, in particular the conditional probability rule, back to the country club example. So here's a table that represents the information that we had from before. As opposed to the Venn diagram, we can have this sort of table that is helpful. There were 10 members that were lawyers and liars, and we were also told that there were didn't want that. We were also told that there were 50 lawyers and 30 total liars. And from that information we saw that there were 20 that were liars but not lawyers. And we also saw that there were 40 that were lawyers but not liars. And recall there was 100 total members, and so that means there's 50 non-lawyers. And here there would have to be 70 non-liars. And so the number that is not a liar nor a lawyer would be, that would need to be 30 there. Okay, that would be 30 there. All right. So let's compute the probability, a conditional probability of A given B. Okay? So if we follow the conditional probability rule, P of A given B, it would be P of A intersect B divided by P of B. Alright, this intersection probability, we've already computed that. Remember, it was 10 out of 100, or we could write it as 1/10. And P of B was 30 out of 100, which we could write as 3/10. And if we simplify that mathematically, we get 1/3. Now we get that by using, what we've done here is we've used the conditional probability rule. Okay. We can also get P of A given B just by looking at the table directly. If I condition on the table directly, okay, so given B has occurred, I'm dealing with just liars. Alright, so this is saying, what is the chance that someone is a lawyer given they are a liar? So if I am just restricting myself to this column here, what is the chance someone is a lawyer given they are a liar? So given they're in this column, they're out of the 30, there's 10 that would be lawyers. And so that would be 10 out of 30, or also 1/3, and that's just by conditioning on the table. Okay, so that's me thinking of conditional probability in the sense that I am going to force the new sample space by looking at that particular column, as opposed to just using the probability rule. The rule always works. Sometimes this works. I say the rule always works. It does. Mathematically, it's always true. Some problems lend themselves to the rule as opposed to just using the conditioning straight up. But I would start with the rule in most problems there. Describe this. What is this group? Well, we're dealing with given B, so B has occurred. We're dealing with lawyers. I'm sorry, let me back up. We're dealing with liars. A represented lawyers, B is liars. And so this is saying that 1/3 of all liars are lawyers. That's how we think of this this conditional probability. 1/3 of all liars are lawyers. Okay. P of B given A. What is that? So we're switching it up here, and if I can just go ahead and condition based on the table, what that would do is, so given A, that means I'm dealing with just the lawyers. So I'm restricting myself just to this top row in the table there. So out of 50, how many are also liars? That's P of B given A. That would be 10 out of the 50 there. Okay, so that would be 10 out of 50, or 1/5. All right, and this is by conditioning on the table again. If you wanted to use the rule, you could, but I just conditioned on the table there. And so what this says is, hey, we're dealing initially with all lawyers, and the chance that one of them is a liar, given that we randomly draw one, is 1/5. And so this would tell us that 1/5 of all lawyers are liars. Okay. Alright, so continuing on here, more with conditional probability. Here is an ad. It's an old ad, but it's from Allstate Insurance. Take a moment to look at that. How is there a conditional statement there? The conditional statement here is drivers who switched. Okay. Allstate has given us information about drivers who switched, not about every driver. All right. So there's two subtle things with this advertisement that Allstate they're truthful in the advertisement, but that's not the main point they want to get across to you. The main point they want to get across to you is this $396, that you save $396. Well, you don't necessarily save that much. On the average, drivers who switched save that much. So the drivers who switched is that condition, and of those that switched, the average was $396. Okay. This number would undoubtedly go down. I say undoubtedly, I'm pretty sure it would go down if you considered all drivers that were eligible for insurance. Okay, not just those that switched. All right. More about probability rules. This idea of independent events. We say events A and B are independent if and only if the intersection probability is P of A times P of B. Now, if that's the case, then let's just kind of follow our noses a little bit. Remember the conditional probability rule. Probability of A given B is always equal to the probability of A intersect B divided by P of B. Now, the definition of independence says that the intersection probability is P of A times P of B. Okay? So, this is, out of space here, let's see. So if A and B are independent, then this equals P of A times P of B divided by P of B. Well, what happens to P of B? It cancels out, so we just have P of A. So what this says is that, and that's what I've got here, equivalently, events A and B are independent if P of A given B is P of A, and if P of B given A is P of B. And so what is this saying here? This is saying knowing information about B does not change the probability of A. Okay, so we think of those events as independent. All right, so if in the baseball example, if Alex Rodriguez, if the probability of him getting a hit is P of A and the probability of him getting a hit given there are men on base, if those two probabilities are the same, or those two batting averages are the same, then we would say that the events of men being on base and him getting a hit are independent of each other. Okay. So let me write this out. Let me flesh this out. This says here that event B does not affect the probability of event A occurring. All right. They are independent. All right, so if we come back to the country club example, are events A and B independent? Are they independent? In other words, does this equality hold for that example? Well, what do we remember? Well, probability of A intersect B is, I'm not going to write it equals this yet. That's only the case if they're independent. I have to verify this equation for independence. But P of A intersect B, if you recall, is 1/10. It was 10 out of 100. And what was P of A times P of B? Well, P of A was, better go back to it. The probability of A was 50 out of 100, 1/10, and P of B was 30 out of 100, or 1/3. So I've got 1/2, 50 out of 100, times 30 out of 100. I said 1/3. I made that mistake earlier. It's not 1/3, it's 3/10. Okay. So this is 3/20. That clearly does not equal 1/10. So A and B are dependent. Okay, are dependent. This equality did not hold, so they're dependent here. All right. In a lot of situations, it's pretty clear that events are independent. So, for example, if I flip a coin 3 times, each flip is not each subsequent flip is not affected by prior flips, and so those events would be independent there. Seeing a head or a tail on a given flip. Alright, so kind of getting off track here. What does this imply regarding the members? That A and B are dependent. That is, that being a lawyer or liar has some effect on the probability of a member being a liar or equivalently a lawyer. Getting both statements in there. Okay, moving along, here's an example, a probability example that ties together several of the rules that we have seen so far. Pretty lengthy example, so you may want to hit the pause button and take a break here. Okay, so you have 2 baskets here. You have basket 1 and basket 2. Warm-up question in part A. Assuming that each chip has an equally likely chance of being drawn, what is the probability that you draw a green out of basket 1? Well, how many are in basket 1? There's a total of, if you want a picture here, basket 1 looks like this. There is a total of 15 red chips and 20 green chips, and you're pulling 1 chip out of that basket at random. The chance that it's green is going to be 20 out of the total there, 35 chips. Okay, so kind of a warm-up there that assumed equally likely events, or outcomes, equally likely outcomes. This one's a little trickier. We got, again, 2 baskets, really. Basket 1 and basket 2. Hopefully you've read through the problem. Again, basket 1 has 15 reds, and basket 2 has 20 greens. 20 greens is in basket 1. Basket 2 has 4 reds and 6 greens. Okay. Now, the thing that's going on here is we're taking a chip and we are drawing it at random and putting it into basket 2. And we don't know what we moved from basket 1 to basket 2. Alright? And then we pull a chip out of basket 2, and we want to know what is the chance that chip is red. So there's kind of this 2-stage experiment going on here. We move a chip from basket 1 to basket 2, and then we pull one out from basket 2. Alright. So let's see. This is kind of a complicated thing, so I'm going to define several events up front to give some clarity here. I'm going to define R1 as the event that you draw a red chip from basket 1. Okay. What's that? Basket. Basket 1. Okay. The subscript 1 denotes we're dealing with basket 1. R tells us it's a red. So I want to contend with that. I also want to contend with I could draw a green one from basket 1. Now, the reason I'm doing that is I want to account for the two possibilities of the first stage of this experiment, that I could be moving a red over to the second basket, or I could be moving a green over to the second basket. And I need to account for both of those. Now, in terms of the event of interest whose probability I'm computing, I'm just interested in a red coming out of the second basket after that first stage has taken place. So I'm going to define this other event R2 as the event of drawing a red chip from basket 2. Okay? So when I think of how could I draw a red chip out of basket 2 in this particular setup, I could draw a red chip out of basket 2 in a couple of ways. I can move a red over from basket 1 to basket 2, then out comes a red, or I can move a green from basket 1 to basket 2, and then out comes a red. So there's two ways in there. I want to account for those. So the probability of the event of interest is equivalent to the probability of, let's think of those two ways. I could move a red from basket 1 to basket 2, and I would have to draw a red out of basket 2. That's one of the ways. So red out of basket 1 and a red out of basket 2. I've got the intersection there. That's one of the ways. Or the union is often thought of as an or I could draw a green from basket 1 and then a red from basket 2. So this represents the two ways here of drawing ultimately a red out of basket 2. So when I think of this here, I've got the probability of this. You can think of that as an event and that as another event. Okay? I have a rule that helps me deal with those sorts of probabilities. This addition rule. Now, I didn't make a big deal out of it earlier. Maybe I should have. But this intersection probability, it becomes 0 if A and B are mutually exclusive. And that's what one of the rules was, one of the properties of probability that we had looked at, that we had listed there. So this equals 0 if, this equals 0 if A and B are independent. Okay. Now, so let's ask the question: are these? Now, I kind of pretend this whole thing in the bracket there is A, and this is like B. Is this event independent of this event? Do they have anything in common? The answer is no, they don't. I said independent. Ooh, pardon me. It was too early. That is 0 if A and B are mutually exclusive. Please forgive me. A and B are mutually exclusive, then that is 0. Alright? Is this event mutually exclusive of this event? In other words, do they have any outcomes in common? Okay. Can this one and this one occur at the same time? And the answer is no, they can't. And so this would be the probability of R1 intersect R2 plus the probability of G1 intersect R2. And I'll just write that out here because R1 intersect R2 and G1 intersect R2 are mutually exclusive. Okay? So, Now I've got these probabilities to contend with. Alright. Probability of R1 intersect R2. If you recall, the multiplication rule from earlier looks something like this. P of A intersect B is equal to P of A times P of B given A. Let's see here. It's also equal to P of B times P of A given P of B. Okay? So I can compute this intersection probability if I think of this problem in the right conditional probability sense. So should I think of R1 given R2 or R2 given R1? All right, thinking about the nature of the problem, it makes sense to think of what's going on in basket 2 given what happened in basket 1. And so I'm going to have a P of R2 given R1, and then out in front is going to be the probability of R1. Okay. And then similarly, I'm going to use the multiplicative rule on this quantity here. I'm going to have the probability of G1 times the probability of R2 given G1. Alright, so what are these probabilities? The probability of R1, drawing a red out of the first basket, is 5/11ths, right? I'm sorry, that's confused here. Is 15 out of 35. The probability of drawing a red out of basket 2, given you drew a red out of basket 1, that's 5/11ths. Now, it's 5/11ths. The basket 2 looks different after event R1. Basket 2 now has 5 reds in it and a total of 11 chips in there. So it'd be 5 out of 11. 5 out of 11. Plus P of G1. We did that earlier. That's 20 out of 35. Okay. And P of R2 given G1. Basket 2, so given G1 has occurred, what does basket 2 look like? Now there's 7 greens in basket 2, still 4 reds, but the overall probability has changed from 4 reds out of 4 plus 7 greens, so that would be 4/11ths there. Okay. So if you do the arithmetic here, you'll see that this is 31 out of 77, or 0.403. Okay, probability rules, part 2.